Hello there. In this video we're going to discuss another useful property of Taylor series, and that's used to approximate the value of definite integrals of functions that do not necessarily have an elementary primitive or ones that you may not want to find or maybe not know directly. So if you do not already know, some functions, for example cosine of x over x, do not have elementary primitives. That is, it's not practical or possible to find a function f of x such that the derivative of it is equal to cosine of x over x. So what if I were to ask, what is the integral under this curve from 3 to 5? Well, if you were to know what this function was, then by the fundamental theorem of calculus, since this function is definitely continuous on 3, 5, the only issue is that x is equal to 0, then you would just say, okay, this is going to be equal to f of 5 minus f of 3, where the derivative of capital F of x is equal to cosine of x over x. But as one may be able to find, this function, capital F of x, does not exist in terms of elementary functions. Even though this answer does exist, we can't find it via the fundamental theorem of calculus. So in this video, we'll discuss how to use Taylor series of functions in order to find approximations for these answers. Alright, so for our first example that we will illustrate with this approach, we're going to consider the integral from 0 to 3 of the function sine x divided by x dx. So this function sine x over x does not have an elementary primitive, so using the fundamental theorem of calculus will not be useful here. So the first thing to observe is that this function does have the function sine x in it, and you should already know what the Taylor series for sine x is. So remember that sine of x is equal to the alternating odd powers of x divided by the factorial of that corresponding term, namely x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus 7x to the 7th divided by 7 factorial plus minus and so on. So since the sine of x is equal to this term, what I'm going to do is divide sine of x by x. So that will give me the Taylor series for sine x over x. So sine of x over x is going to be equal to 1 minus x squared over 3 factorial plus x4 over 5 factorial minus x to the 6 over 7 factorial plus or minus and so on. So what I'm going to do is I'm going to integrate with respect to x of those functions. So that's going to give me the integral of sine x over x dx is going to be equal to the integral of 1 is just going to be x. The integral of x squared is going to be x cubed over 3, so that's going to give us x cubed over 3 factorial 3, and then plus x5 over 5 factorial 5, minus x to the 7th over 7 factorial 7, plus or minus, and so on, plus some arbitrary constant c at the end. Alright, so now I'm going to find my solution to the problem I have. So if this is the case, the integral from 0 to 3 of sine x over x dx must be equal to this expression evaluated at 3 minus that expression evaluated at 0. So when x is equal to 0, this whole entire term is going to go to 0 because each of those terms has an x in it, and we're not dividing by x here, so we don't have any issues there. So the only value that's going to contribute anything is this value that we get at 3. So that means this is going to be equal to the sum from k is equal to 0 to infinity of -1 to the k times x to the 2k plus 1 divided by 2k plus 1 factorial times 2k plus 1, and we're going to take this expression and evaluate it at x is equal to 3. So if that's the case, that means the integral from 0 to 3 of sine x over x dx is going to be approximately equal to the sum from k is equal to 0 to capital N of negative 1 to the k times 3 to the 2k plus 1 all over 2k plus 1 factorial times 2k plus 1, where n is large. Like 100, 1000, depends on how accurate you want, and you can figure out how fast that converges. So this is my approximation to this integral, and if you choose n to be equal to large, you'll figure out that this is going to be approximately equal to 1.849. So that is one example of how to use Taylor's series to approximate. Let's do another. So another example, so example 2, suppose we want to approximate the integral from 0 to 5 of e to the minus 1/2 x squared dx. So I'm going to begin by realizing that this is an exponential function, and I should know the Taylor series of that. So since e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus and so on, then we have that e to the minus 1/2 x squared is going to be equal to e to the negative. So how can I figure out what this? So I'm pretty much replacing x with that expression. So therefore, this is going to be 1 plus negative 1/2 x squared plus negative 1/2 x squared over 2 factorial plus negative 1/2 x squared cubed over 3 factorial plus negative 1/2 x squared to the 4th over 4 factorial plus and so on. So let's clean this up just a tad bit. So we have e to the minus 1/2 x squared is going to be equal to, so we have 1 minus 1/2 x squared. So when we square a negative, it's going to be positive, so we're going to have plus 1/2 squared, which is 1/4, but I'm going to write it in this way temporarily, because we might see a pattern if we keep it that way. It's going to be x to the 4 over 2 factorial. So when you cube a negative, it's going to be negative, so we're going to have negative 1/2 cubed x to the 6th over 3 factorial. Take a negative number, raise it to the 4th, it's going to be positive, so we're going to have positive 1/2 to the 4th. So we have 4 factorial, so how can we express 2 to the 4th, which is 8? So that's going to be x to the 2 times 4, plus or minus, and so on. So now I can figure out, okay, how can I express this in terms of a Taylor series? So I can rewrite this as e to the 1/2 x squared is going to be equal to the sum from k is equal to 0 to infinity of negative 1 to the k, because it starts at positive, negative. Then we have this 1/2 constant raised to some power k, and then times x to the 2k, because we have 0, 2, 4, 6, 8, and so on. And the factorials on the bottom is going to be 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on. So we have just k factorial there. So this is going to be the Taylor series of my function of interest. So now I'm ready to find the definite integral of my desire. So we have the integral from 0 to 5 of e to the minus 1/2 x squared dx is going to be equal to the integral from 0 to 5 of this Taylor series. So the sum from k is equal to 0 to infinity, negative 1 to the k, 1/2 k, x to the 2k over k, factorial dx. So notice the only thing that has x in it is this expression, so everything else I can sort of factor out. Summations and integrals can switch because they're not of the same interest. This is of k and this is of x. And there's another theorem that pretty much dives into the detail of when you can switch, but that's pretty much the basic idea that you need to know. So this is going to be the summation from k is equal to 0 to infinity of negative 1 to the k, 1/2 to the k, 1 over k factorial times the integral from 0 to 5 of x to the 2k dx. So I can apply the power rule on this expression here. So that's going to give me, so the integral from 0 to 5 e to the minus 1/2 x squared dx is equal to the sum from k is equal to 0 to infinity, negative 1 to the k, 1/2 to the k, times, so we're going to raise the power by 1, so we have 2k plus 1, divided by, so we have the k factorial, and we have the 2k plus 1 constant. And what we need to do is evaluate this as x goes to 5 and as x goes to 0. So x goes to 0 is going to send this whole entire thing to 0, so that's not going to contribute. So we just need to plug 5 in, and that's going to be our value. So we have the integral from 0 to 5 of e to the minus 1/2 x squared dx is going to be the sum from k is equal to 0 to infinity of negative 1 to the k, 1/2 to the k, times 5 to the 2k plus 1, all over k factorial times 2k plus 1. And using your integral tests for convergence, you can figure out, or your other comparison test and limit test and so on, you can find that this series definitely does converge to something. So I can choose an arbitrarily large number n, so let's assume n is large, like 1,000,000 or 1,000, depending on what type of accuracy you want. Then we have that the integral from 0 to 5 of e to the minus 1/2 x squared dx is going to be approximately equal to the sum from k is equal to 0 to capital M, where n is large, of the alternating series 1/2 to the k, 5 to the 2k plus 1, all over k factorial 2k plus 1. And if you choose n to approximately be large, then you can have the approximation 0 to 5 e to the minus 1/2 x squared dx will be approximately equal to 1.2533. And if you're really feeling ambitious, I even challenge you to find the exact value of this value. You know, that's another thing to discuss. So for right now, we'll just leave it at here. But I'm just going to tell you anyway. This should be approximately equal to the square root of pi over 2. Now, this is not exactly what square root of pi over 2 is, but it's an interesting observation that this is going to be approximately equal to that. This dives into probability theory and statistics, but that's another discussion for another day. But this is pretty much how you can use Taylor series to approximate the values of definite integrals for which the elementary primitive might not be able to be obtained.